Hi, my name is Barry Setterfield. Welcome to this first session in a two-part series on catastrophic events in the solar system. Initially, it had been thought that all the craters that we see on the inner planets and on the moons throughout the solar system were caused by the debris, the leftovers from the formation of the solar system, raining down on these objects. However, in the last year, it has been determined from the data that there is in fact a timeline dating these events. It was not just one event. And interestingly, when the data is considered, it all links in with what we find in Earth geology. And so in this first part of the two-part series, we're going to examine what caused this chaos and what was the outcome of it. And then in part 2, we'll be considering the timeline, which gives us a few more clues as to what actually happened. So let's get started. On the 15th of February 2013, an asteroid 20 yards across exploded over the Urals in Russia. It left the vapour trail seen here. The explosion had the strength of 25 Hiroshima bombs. 1,500 people were seriously injured and 7,200 buildings were damaged. The object entered the atmosphere at 42,000 miles per hour. The resulting explosion, shown here, was brighter than the sun. One of the pieces that was left after the explosion impacted on the frozen surface of a lake near Chelyabinsk, leaving this 50-foot diameter hole in the ice. Later, this 1,250-pound meteorite fragment was pulled from the bottom of the lake there. Before it had broken up, it was over 5 feet across. In a different incident, on the 7th of September 2014, a 60-foot asteroid passed 25,000 miles from the Earth. This is just 1/10 of the distance of the Moon from the Earth. In fact, it passed by just outside the orbits of the geostationary satellites. But that was not the full story. In the late evening of the 6th of September, the previous day, some debris associated with that asteroid impacted in a forest near Nicaragua's International Airport. It left this crater. There is no doubt that such impacts result in craters. Because of the energy involved, no matter what angle the object comes from, the resulting impact explosion will leave a circular crater. In fact, we can illustrate this by experiment. Since any material will be smashed to dust in a real impact, we used a pan of cement dust 4 or 5 inches deep as the ground for the meteorite or asteroid to hit. Since the meteorite is also pulverized, we use a medium-sized spoon of slightly compressed cement dust as an impact ore that is dropped from a height of about 4 feet. The results of such impacts, plus splash craters and rays, can be seen here. The ridge line comes from the surface preparation after the previous experiment. Because of a potential impact disaster, astronomers are trying to track dangerous asteroids and similar solar system debris, but they can't get all of them. Some are hidden by the sun. We don't know they exist until too late. Since they come at us from the direction of the sun, they are impossible to detect. The Catalina Sky Survey instruments on Mount Lemmon, Arizona, shown here, and other similar facilities are finding new objects at the rate of 30 per week, or about 1,500 per year. The current catalogue of asteroids crossing the Earth's orbit is about 19,000. Asteroids and related solar system debris range in size from specks of dust through grains of sand and house-sized pieces up to objects 590 miles across. Many of these pieces are potato-shaped. If a larger one of these pieces came near the Earth and was pulled in by our gravity, the threat from impact is real. For example, we find a crater in the rock strata in Mexico, whose location is shown on the upper left and enlarged on the lower left. Analysis of the geological strata, bottom centre, reveals a 120-mile wide double-ringed crater. Its appearance at the time of formation is shown in the upper right. The structure was formed by an object 10 miles wide and moving at 10 miles per second. This object was part of a shower of 7 other large pieces of solar system debris which wiped out the dinosaurs. A much smaller piece of debris, only 100 yards or so across, can leave a crater like this one in Arizona, seen on the left. That is because at the moment of entry into our atmosphere, such an object can be travelling anywhere from 7 up to 45 miles per second. If a similar object hit Manhattan, the result might be something like the image on the right. The wildfires, earthquakes and tsunamis mean devastation worse than any hydrogen bomb. These facts lead us to ask 2 questions, whose answers bring some hidden solar system truths to light. The first question is, where do these objects, this solar system debris, come from? The second question follows naturally. How did these objects originate? In answer to the first question, we know there are 2 belts of solar system debris, one close in, the other far out. The one close in is called the asteroid belt. It exists mainly between the planets Mars and Jupiter and is marked by a yellow arrow here. However, the process which formed this debris caused some significant amount of it to orbit closer to the Sun, the red and blue arrows. The Earth still runs into this debris. They are a portion of the meteors which often enter our atmosphere. Also, some others orbit as far out as Jupiter, and some are actually in the orbit of Jupiter itself, the white arrows. The 4 largest asteroids are shown here. They all inhabit the belt between Mars and Jupiter. Ceres, the largest, is 587 miles across. Then follows Vesta, Pallas and Hygeia, the smallest of the big 4, at 271 miles across. The rest of the inner debris belt, or cloud, range from 270 miles across down to specks of dust. It is thought there are 2 million objects larger than half a mile across. The second extensive debris cloud is out beyond the orbit of Neptune and is known as the Kuiper belt. Pluto is part of this group of material. Its orbit is shown here. It is much more elliptical than the major planets and at quite an angle to the plane in which the major planets move. Both these features are typical of Kuiper belt objects, which are also called trans-Neptunian objects, or TNOs. Pluto has 5 satellites orbiting around it. This too is typical of these objects. Here are the 8 largest Kuiper belt objects. To date, Pluto and Eris, with their attending satellites, are the biggest found, being about 1,400 miles wide. This is about half the size of our Moon. Currently, we have found several thousand objects in the Kuiper belt, but it is estimated that there are over 100,000 objects larger than 100 miles across. Likewise, it is estimated that there are over 100 million objects that are less than 20 miles across. Among this group of objects are comets, like Comet McNaught seen in Australia in 2007. The orbits of many comets show they originated in the Kuiper belt and are part of the entourage of debris which is found there. Some comets get their orbits changed by interaction with the giant planets as they come through the inner solar system. They are captured by this process and stay inside Pluto's orbit as short-period comets. The debris-littering comet orbits also give us meteor showers. So the answer to the first question is that there are 2 debris belts in the solar system, the asteroid and Kuiper belts. they have literally thousands of objects which could potentially travel into the inner solar system as showers of debris with catastrophic consequences. The second question asks how these clouds originated. As it turns out, there are two possible origins for the belts. The first is that a single planet never formed because Jupiter and Neptune prevented it. This is a possibility because the gravitational strength of both Jupiter and Neptune, coupled with their orbital motion, would throw particles from their orbits. This process could prevent large objects from building up in either belt. We must emphasize this is the usual explanation of standard astronomy. However, the second option is that there was originally a planet and moon where each of the belt now exists, but they exploded and showered the solar system with all the debris. This second option is now being seriously considered by some astronomers after being put on a solid footing by the late Dr. Thomas Van Flandern of the US Naval Observatory in Washington. He's seen at the right there. 4 lines of evidence suggest that such explosions occurred. First, when the Chinese exploded their Fengyun 1C weather satellite over the North Pole on the 11th of January 2007, the orbits of fragments larger than 2 inches were graphed. After 6 months, the orbits of the debris ranged in altitude from 200 to 4,000 kilometres, but all the orbits crossed at the explosion point, as shown here. This is now an expected result for explosions in orbit. When Van Flandern plotted the orbits of comets that originated deep in the Kuiper belt, he noticed that the orbits generally seem to intersect at a specific region in the outer solar system. In 2012, it was noted that Kuiper belt objects which go out the farthest, like Sedna, show a similar effect as graphed here. Their meeting point is near the closest part of their orbit to the Sun. That point is twice as far from the Sun as Pluto is. Yet this suggests that any parent planet may have exploded near there sometime in the past. Second, an explosion is suggested by the dark residue on some moons in the outer solar system, like Jupiter's moon Callisto and Saturn's moon Iapetus. Their surface was darkened as the blast wave travelled through. Thus, the leading edge of Iapetus, shown on the left here, is covered with a brownish deposit, while the untouched surface is whitish. Shadows are black. Third, there is a problem posed by binary or multiple systems, which should be rare according to the standard model. A maximum of 1 in 10 objects should be like that, but in the asteroid belt, at least 1.6 times that number of objects are binary or triple systems with small moons in orbit around them. Here's the asteroid Florence, imaged with 2 moons, an inner and an outer moon. The number of examples is increasing as many more examples are being found. In other words, 2 or 3 fairly large pieces of asteroid or space rocks are circling each other in their orbit around the Sun, or have their own tiny moons circling them. It gets worse in the Kuiper belt, whose objects are also known as trans-Neptunian objects. Here is a selection of the 10 largest. All but 2 of them have moons, and Pluto, in fact, is a 6-body system. It seems normal for objects in this belt to have 1 or more moons or be part of a double or multiple system. These data present severe difficulties for the standard collision model, which expects only 1 of these 10 bodies to be like this. Instead, it seems to be the rule, not the exception. The standard model states there were originally large numbers of objects in both the asteroid and Kuiper belts. These objects collided with each other, and the resulting debris formed what we see today. larger objects with smaller objects or moons orbiting them. The reason this standard model fails is that when two objects collide in space and shatter each other, this process generally accelerates the debris particles to speeds which cause them to escape the colliding body's gravity entirely. Instead of that, what we can see are rubble piles like the asteroid Itokawa shown here, plus asteroids with moons. As it turns out, one of the most basic indicators of the explosive disruption of a parent planet is the entrapment of debris around larger or more massive objects. This happens because the region around the explosion is initially thick with debris. Many pieces would find other fragments within their own gravitational sphere of influence and retain them long term. The fourth piece of evidence for the explosion model is the composition of the asteroids. They circle the Sun in three main groups or bands. These bands in the asteroid belt have different compositions. The inner main belt asteroids are mainly silicates or stony, like planetary mantles, and crust with a bit of iron. The central belt is made up of metallic asteroids, like planetary cores. The outer belt is primarily a carbonaceous mixture, like a moon. Here we see these things diagrammed differently. The vertical scale is the number of asteroids. The horizontal scale is the distance from the Sun in astronomical units, or AU, where 1 AU equals the Earth's distance from the Sun. Thus, the greater distance from the Sun is further out to the right. Here are the three main groups of asteroids that can be seen with the gaps between them. The composition suggests the mantle, the core, and the moon of a planet going out from the Sun through the main asteroid belt. At this point then, the evidence does strongly support the model which states that there were two other planets which exploded, one between Mars and Jupiter and the other outside Neptune's orbit. So why would these planets and their moons have exploded? There was no satisfactory answer to this question before the late 1970s and the space age. But by the 1980s, data had accumulated which suggested a reason quite different from the only viable explanation accepted before. Analysis of the meteorites from the asteroid belt reveals that a large amount of some radioactive elements were present on the parent body. As they rapidly decayed, they heated that parent body. The Cambridge Atlas of Astronomy points out that if this body was greater than 10 kilometres across, this heat would be great enough to melt it. As rock melts, it gains 10% in volume. So this evidence suggests the internal pressure was building during this heating process. The second piece of evidence also comes from the asteroid belt meteorites. They show that the parent body had up to 20% water locked up in its mineral structure and composition. But heat had released that water, which then altered both the mineral grains and their matrix, as seen in the centre of the right image. There the mineral grain is disintegrating and has a dark band of chemically altered material around it from the action of hot water. By comparison, the grains on the left image are sharp and unaltered. So radioactivity and hot water are two keys. We now need to see how this worked to produce an explosion. In our previous sessions, we have presented strong evidence that the universe did not form by gravitational action, but by the interactions of plasma filaments and sheets. We know now that over 99% of matter in the universe is in the form of plasma. In space, gravity is a very weak force, but the electromagnetic interactions in plasma are very much stronger. The standard model of the solar system's origin has a huge disk of material around a central sun. Within that disk, multiple massive collisions eventually formed the planets. That model says all planets started off extremely hot and then cooled. This image is the model's expected conditions for the early Earth. After planet formation, the leftovers from the disk continued to rain down on the planets and moons until the leftovers were totally depleted. Many craters formed as a result. However, the plasma model says that we did not start hot, but cool. Here is why. Everything began with plasma filaments in space. Every plasma filament carries an electric current with a circling magnetic field, as sketched on the left. But the magnetic field is unstable. Any change in current flow or temperature, and the field will fork or twist and pinch in. This happens to a metal can that was carrying a current. We also see this in lightning. Out in space, when filaments pinch, they form a plasma ball called a plasmoid. Because the electric current flowing in the filament becomes focused on the plasmoid, it lights up and becomes a star. This can be seen in detail with three individual examples on the left: the Ant Nebula, the Butterfly Nebula, and the wings of a butterfly nebula. On the right, Orion plasma filaments are all pinching to form stars, the bright spots, like beads on a string. The filament which formed our solar system split into a number of subfilaments and started pinching, as in this lab example on the left. There, the pinches formed the bright spots on the subfilaments at the top. In the case of the solar system, right, the outside subfilaments showed the pinch effects first, as little balls were formed and started spinning and orbiting the centre. As the pinch moved into the centre from every direction, the centre was compressed, and finally our sun lit up. Then what develops from the data and plasma physics has to do with something called Markland convection. This is a reference to the sorting of elements in the original solar system plasma filament. Of the many elements which made up the filament, those which released their electrons most easily, like iron and nickel, collected in the centre of the filament, giving it a more positive charge. On the other hand, those elements which retained electrons strongly, like nitrogen, gathered on the outside, giving it a more negative charge than the centre. The order of sorted elements from the centre of the filament out to its edge is shown here. Thus, planets near the Sun, near the centre of the solar system filament, should have a high percentage of nickel iron, and so have large cores in comparison to the size of the planet. Those further out should predominate in carbon, hydrogen, oxygen and nitrogen, with small metal silicate cores surrounded by those gases. Therefore, we'd expect ever higher water content the farther out we go. We find this is the case when we compare the structure of the inner and outer planets. This process meant all planets started off layered and cool, with radioactive elements concentrated in their cores and mantles. The physical evidence is presented in the session on the Bible and geology. Rapid radioactive decay then heated the planetary interiors. This did two things. First, it melted the metallic cores, which gained 10% in volume. Second, it drove water from the interior to the surface. Data show a 20% water content for asteroid parent bodies. Pressures from these two processes were enormous, and the asteroid planet and its moon exploded. The Kuiper Belt planet was also layered. The sorting sequence indicates its composition was comprised of ices and frozen gases with a rocky core containing radioactive elements. As the radioactive decay occurred, the planet heated up. Because its interior had a high percentage of frozen methane, ammonia and carbon dioxide, these ices rapidly vaporized and put pressure on the structure of the whole planet, which then shattered. Why didn't the other planets explode? First, the percentage of water locked up in planetary interiors increased out from the Sun, according to Markland convection. Thus, the atmosphere of Venus has 120 times the deuterium from water in planetary interiors that the Earth has. It must have been poured out as an eruptive episode or episodes. Mars has outflow channels shown here, where it was considered that 1/3 of the volume of the Indian Ocean was outpoured in 8 weeks to make a northern ocean. In the Bible and geology, we show a massive outgassing of water from Earth interior occurred during the snowball Earth event in the Cryogenian period of the Archaeozoic era. After the asteroid belt, we see the 4 gas giants. Their cores are molten nickel iron and silicate rock surrounded by melted water ice. The mantles are liquid metallic hydrogen and liquid molecular hydrogen, which placed enormous pressure on the water. Also, liquid metallic hydrogen conducts core heat away quickly, so no explosion was possible. However, Pluto has a structure typical of Kuiper Belt objects. It is a rocky silicate core, a water ice mantle, and a crust of ices of methane, nitrogen, and carbon dioxide. It is so cold out there that the whole original planet was frozen, including its gaseous envelope. Thus, when the internal heating by its radioactive elements occurred, the entire planet exploded. There is one other factor which is involved in this. Our Sun Puzzles video showed that the positively charged particles that comprise the solar wind speed up the farther out in the solar system it goes. This is because our plasma filament has a negative charge on the outside, as Markland convection or Markland sorting suggests. We're the 3rd planet out from the Sun. That means we're a bit more negative than the Sun. As we go farther and farther out, the negative potential increases. This means that objects coming in from the Kuiper Belt will carry a strong negative charge compared with the rest of the solar system. Lightning here on Earth occurs in order to even out positive and negative charges, either between clouds or between clouds and Earth. In the same way, when objects from the outer solar system approach the inner solar system, strong lightning bolts may occur. This is also true for asteroid belt debris. If the debris is coming towards the inner solar system, it will have a more negative charge compared to us. But if it is flying out towards the outer solar system, its charge will be more positive in comparison to the objects out there. We also see massive lightning discharges during volcanic eruptions, as the photo on the left shows. This is the same thing on a smaller scale. The violence of the eruption is stripping electrons from atoms, resulting in strong positive and negative charges that the lightning equalizes. In the same way, lightning would be involved in the breakup of solar system bodies, as depicted on the right, but this time on a planetary scale. In our solar system, the charge differential itself has decreased with time, so lightning discharges were stronger in the early universe. This is due to the changed electric and magnetic properties of space as the universe expanded. But such activity still continues. For example, electric discharges or lightning still frequently occurs between Jupiter and its inner moon Io. Today, the potential difference between them builds up to 400,000 volts, and a current of 3 million amperes is involved. So we would expect to find evidence of both impact cratering and lightning discharges on planets and moons from the debris expelled by exploding planets. The craters from electrical discharges are referred to as electric discharge machining, or EDM craters. Lab experiments have allowed us to differentiate the characteristics of these EDM craters and those from impact. The top three images here come from EDM craters in the lab in soil, sand and steel. They characteristically have flat floors and vertical walls, and sometimes have a central peak. The lab image at the bottom left shows a discoloration due to high current. Some craters in the photos from Mars and Mercury at the bottom right show all these features. In part 2, we'll be seeing the evidence on planets and moons for both types of cratering, as well as volcanism. So we have seen what happened to produce these craters throughout the entire solar system, how and why. The next big question is, when did these events occur? One way of determining this would be to get rock samples and date them from all of these objects, but currently we're not able to do that. However, there are other methods of determining when this actually happened. And in part 2 we'll be looking at this and how it all links in with Earth geology in an amazing way. So stay tuned. Thank you for your time.